Finite difference approximation of Maxwell's equations on a Yee grid. This is going to be a long and tedious video. Sorry about that, but it is probably the most important video when we're talking about solving Maxwell's equations with finite difference method. Hopefully I can make up for some of that tediousness with the graphics that I put into this. I work very hard to visualize the math that I'll be trying to explain. The first thing we'll do here is discuss our starting point. We're going to normalize our grid coordinates, get the equations all ready for the finite difference approximations. Then we'll go through the three finite difference approximations for our first curl equation, and then the second three finite difference approximations for our second curl, and then we'll summarize that in one slide. Seems like not a whole lot, but let's get into this. The starting point. Up to now, we have a set of 6 equations. These top 3 came from one curl equation and the bottom came from another. We have normalized our magnetic field, which then gave us a K naught over here, and these mu and epsilons are the relative permeability and relative permittivity. And that's where we are now. The next thing we would like to do is normalize our grid coordinates. So our grid coordinates x, y, and z, we will multiply by K naught. Remember, K naught, the free space wave number, is 2 pi divided by wavelength. So we're essentially dividing our grid coordinates by wavelength, so we can think of these normalized grid coordinates as being in terms of wavelength. The only difference is there's this factor of pi sitting here. If it weren't for that, then we would be interpreting our grid coordinates as, if it was a 3, we would interpret that as 3 wavelengths. However, we have that factor of pi there. Not such a big deal, but we have a good reason for doing that. When we apply those normalized grid coordinates to our equations, this is our new set of equations, and the K naught term has completely, I'll say, dropped from the equations. That's not completely true. It got absorbed into these normalized grid coordinates. But this is a greatly simplified set of equations without that K naught term sitting there. And that's why we chose K naught and not just dividing by wavelength. Numerically, they're roughly equivalent, but mathematically, I think it's a simpler equation and a little bit more convenient. So here is finally our starting point. We will proceed with these equations. I have color-coded the electric fields blue and the magnetic fields red. So those colors correspond also to the vector components that we keep showing in the Yee cell. I'll point out one last time. Notice these are not fully anisotropic tensors that we have. These would be called diagonally anisotropic tensors. So we can account for some anisotropy, but these are just the terms down the diagonal. Including the other terms involve some other complications that we don't want to get into here. But we can have some degree of anisotropy. And in fact, our uniaxial PML will enter this and will require a diagonally anisotropic medium. So we're all set up for that. Okay, given this starting point, let's dive into this. Finite difference approximation of the curl of E equals mu H. Well, here's our first equation. We're going to call this the equation for Hx. And yes, this equation has nothing more to do with Hx than any of the other terms in this equation, but it will be very convenient to think that way. And so one thing, here's Hx in our Yee cell. We have a rule for finite difference equations. We want all terms in a finite difference equation to exist at the same points in time and space. We have no time here, so we're only concerned about space. So we're going to make all of the terms exist at the same point where Hx exists. The terms on the left is calculating the curl of the electric fields, and I've drawn this curl that's following the right-hand rule around Hy. So if you take your right hand and point your thumb in the direction of Hx, your fingers will curl in this direction. And the electric fields are lying along this curl path. Okay, so let's get started with this. So everything now becomes a three-dimensional array on our Yee grid. And so we now have these array indices, I, J, and K. So H sub x is a three-dimensional array now. We have the relative permeability multiplying that, mu xx, we need all terms to exist at the same point in space. So since that's multiplying hx, we will define our permeability mu xx to exist at these same points as hx. Now on to the first partial derivative. This is the partial derivative of EZ with respect to y. So we come over here, we find EZ in our Yee cell, and we would like to calculate the derivative in the y direction. And we want to use a central finite difference, and we want that central finite difference to exist where hx exists. That means we need to get the electric field from exactly the other side of the magnetic field. That means we need EZ from the next cell over in the y direction, thus the j+1 array index. So our finite difference approximation would read as EZ from the next cell over minus EZ from the same cell divided by the spacing between them. And since they're spaced along the y-axis, the spacing is delta y. So that's how we write our finite difference approximation. It's the electric field from the next cell over in the y direction minus the electric field in the same cell divided by the spacing in the y direction, which is delta y. And it's actually delta y prime because that's a normalized delta y, but I probably won't bother to mention that again. But that is definitely a normalized grid resolution parameter where we've multiplied by k naught. Now on to the second partial derivative. It's the partial derivative of EY with respect to z. So we come over to our Yee cell, we find EY, and we want the derivative in the z direction using a central finite difference. Well, if we want that central finite difference to be defined where hx exists, we need to utilize an electric field from the other side of the magnetic field, and so we are looking for EY in the next cell up in the z direction. So our finite difference approximation would read the electric field EY from the next cell up minus EY from the same cell divided by the spacing between them, which is delta z. So that's EY from the next cell up in the z direction minus EY from the same cell divided by the cell size in the z direction, which is delta z or delta z prime. And since this is a central finite difference, it exists at the midpoint between these two electric fields, which is right where hx exists. So all terms in that equation exist at the same point in space. And we're ready to go on to the next equation. This is the equation for h sub y. So we look over our Yee cell. Here's h sub y, and I've written where the curl would be happening, and so it's involving the electric fields immediately adjacent to it. So our HYs will exist at this point in all of the Yee cells. Since our mu YY term is multiplying HY, we will define this array to exist at the same points as HY because we need all terms in a finite difference equation to exist at the same point in space. Now let's go on to the first partial derivative. This is the partial derivative of EX with respect to Z. So we go over to our Yee cell, we find EX, and we want to calculate the derivative in the Z direction with a central finite difference. But we want that central finite difference to exist where HY exists. That means we need to reach to the other side symmetrically over HY, which gives us EX in the next cell up in the Z direction. So now our finite difference approximation will be EX from the next cell up in the Z direction minus EX from the same cell divided by the spacing between them, which is delta Z, the Yee cell height. So that's how we write our finite difference. It's EX from the next cell up in the Z direction minus EX from the same cell divided by the spacing, which is delta Z. On to our last partial derivative, the partial derivative of EZ with respect to X. So we go over to our Yee cell, we find EZ. We want the derivative in the X direction. We want to use a central finite difference. We want that central finite difference to exist at the same point as hy. So we need to reach to the other side of hy, and that brings us to ez from the next cell over in the x direction. Now our finite difference approximation would be ez from the next cell over in the x direction minus ez from the same cell divided by the spacing between those 2 points, which is delta x. So our finite difference approximation is ez from the next cell over in the x direction minus ez from the same cell divided by the spacing. And all terms in this equation exist at the same point in space. And our last equation for this particular curl equation, this is the equation for hz. We come over to the Yee cell, we find hz. We can also find the curl path that passes through all the electric fields that are immediately adjacent to it. And so we know that we want all terms to exist right where this hz term exists. So we have our hz array. Our mu zz array is multiplying hz, so we want to define our mu zz array to exist at the same point as hz. So our mu zz's will be right here as well. On to the first partial derivative, the partial derivative of ey with respect to x. So we'll go over to our Yee cell and we find our ey, and we want the partial derivative in the x direction. We would like to use a central finite difference to approximate that, and we want the central finite difference to exist where hz exists. So that means we have to reach to the other side of hz, and now we need ey from the next cell in the x direction. So our finite difference approximation would be ey from the next cell in the x direction minus ey from the same cell divided by the spacing between them. And since this is in the x direction, that spacing is delta x. So here's how we write that. Ey from the next cell in the x direction minus ey from the same cell divided by delta x. And our last partial derivative, the partial derivative of ex with respect to y. So we come over here, we find ex in our Yee grid, and we want to approximate the derivative in the y direction using a central finite difference. We would like that central finite difference to exist right where hz exists, so we need to reach to the other side of hz, which means we need ex from the next cell over in the y direction. So our finite difference approximation would be ex from the next cell over in the y direction minus ex from the same cell divided by the spacing between them, which is delta y because this is happening in the y direction. So we have ex from the next cell over in the y direction minus ex from the same cell divided by delta y. And all terms in that equation exist at the same point in space. Finite difference approximation of curl of h equals epsilon e. So here's our first equation to write the finite difference approximation for. And we're going to call this the equation for ex, even though it has nothing more to do with any other variables than ex. But it makes sense to do that because we're going to define all the terms in this equation to exist where ex exists. And we go to the Yee grid, and here is our ex component. So all terms in this finite difference equation, we want to exist at this point. And of course, the terms on the left is calculated the curl, and I've sort of highlighted where the curl path would be. And so we need to look at the adjacent magnetic fields to do that. So right away, we know that ex will be an array, and we have array indices I, j, k. So, and this ex will be defined to exist right here. So therefore, the relative permittivity epsilon xx, since that's associated with ex, will be defined at the same point. So our epsilon xx's will also be at the same point in the Yee cells. So we want all terms in this equation to exist at the same point as ex. Let's proceed. The first partial derivative is the partial derivative of hz with respect to y. So the derivative in the y direction. So here's our hz term, and we would like to calculate a derivative in the y direction. Now, if we're doing this with a central finite difference, and we want that finite difference to exist where Ex exists, we have to reach to the other side of it. Now, in this case, it's a magnetic field from the previous cell. So the way this will work, our finite difference approximation would then be the magnetic field from the same cell minus the magnetic field Hz from the previous cell in the y direction divided by the spacing between those points, which is delta y. And that finite difference would exist at the midpoint, which is right where Ex exists. So we have now the magnetic field from the same cell minus the magnetic field from the previous cell in the y direction divided by the spacing in the y direction. Now this is in contrast to the previous set of three equations where it was always electric field from the next cell minus electric field from the same cell. This has changed. Now it's magnetic field from the same cell minus magnetic field from the previous cell, and it changed due to the staggering on the grid. Let's go to this next partial derivative, the partial derivative of hy with respect to z. So here's our hy, and we want the derivative in the z direction. We're using a central finite difference, and we want that finite difference to exist where Ex exists. So we have to reach to the other side of Ex, and so in this case, it's from the previous cell in the z direction. So our finite difference would be the magnetic field Hy from the same cell minus Hy from the previous cell in the z direction divided by the spacing between those points, which is delta z, the cell height. So here's our finite difference. Magnetic field Hy from the same cell minus magnetic field Hy from the previous cell in the z direction divided by the cell size in the z direction, which is delta z. That's a central finite difference and exists at the same point as Ex. So that whole equation is in harmony. On to the equation for Ey. Here's our Ey component. So we would like all terms in this finite difference approximation to exist right where Ey exists. So of course, Ey exists where Ey exists. That doesn't even need to be said. But since our permittivity, epsilon yy, is multiplying Ey, we're going to define epsilon yy to exist at the same point. So our epsilon yy will be taken from these points in the Yee cells. Now on to the derivative of hx with respect to z. So here's our hx, and we want the derivative of that in the z direction. Using a central finite difference that we want to exist where Ey exists, we have to reach to the other side of Ey, which in this case is hx from the previous cell in the z direction. So our finite difference would be hx from the same cell minus hx from the previous cell in the z direction divided by the spacing between those 2 points, delta z. So this is how we write the finite difference. Hx from the same cell minus hx from the previous cell in the z direction divided by the cell height, delta z. And our last partial derivative in this equation is the partial derivative of hz with respect to x. So here's our hz component in our Yee cell, and we want the derivative in the x direction. We would like to use a central finite difference. We would like that central finite difference to exist where Ey exists. So we need to reach to the other side of the cell, and here it's hz from the previous cell in the x direction. So our finite difference equation will read this way: hz from the same cell minus hz from the previous cell in the x direction divided by the spacing between them, delta x. And we write our finite difference equation this way: hz from the same cell minus hz from the previous cell in the x direction divided by the spacing delta x. And so all terms in that finite difference equation exist at the same points as Ey. So they're all at the same points in space. Our last equation, the equation for Ez. So here is Ez in our Yee grid, and we want all terms in our finite difference equation to be defined there. So here's our EZ defined at this point. We see an epsilon ZZ multiplying that, so we're going to define our epsilon ZZ permittivity array to exist at the same points as EZ. On to our first partial derivative here, the partial derivative of HY with respect to X. So here's our HY in the Yee cell, and we want the derivative in the X direction. Well, if we're using a central finite difference, and we want that central finite difference to exist where EZ exists, we need to reach to the other side where HY is in the previous cell in the X direction. So our finite difference would read HY from the same cell minus HY from the previous cell in the X direction divided by the spacing between those points, which is delta X. So here's our finite difference approximation. HY from the same cell minus HY from the previous cell in the X direction divided by the spacing delta X. That's a central finite difference that exists at the same point as EZ. And our last partial derivative of HX with respect to Y. So here's our HX, and we want the derivative in the Y direction. If we're using a central finite difference that will exist where this EZ exists, we need to reach to the other side, in which case that's HX from the previous cell in the Y direction. So our finite difference approximation would be HX from the same cell minus HX from the previous cell in the Y direction divided by the spacing between those, which is delta Y. And here's our finite difference approximation. HX from the same cell minus HX from the previous cell in the Y direction divided by the spacing delta Y. And so all terms in that finite difference equation exist at the same point as EZ. So that entire equation is also in harmony. Summary of finite difference equations on a Yee grid. In one slide, this is what we've done. We've gone from a set of 6 coupled partial differential equations. We went one at a time, looking at the Yee cell and how the field components lie, and we wrote these finite difference approximations. And these are all very simple approximations. They're very compact, so they're very accurate, and they incorporate all the information from the Yee grid, so they're divergence-free. And now these are ready to be solved by a variety of methods, which comes in following lectures.